Hello, guys. Welcome to another episode of Cuda Education. So we're continuing our discussion of the heap as it relates to texture and textured material. Okay, so just to recap real quick, it's a big block of code. I'm sorry, a big block of memory that is sort of taken out of GPU memory, and then inside of that block we have sub allocations. And then the two big advantages of doing it this way as opposed to not using a heap where you're just randomly assigning allocations across the whole memory space and all that stuff is that residency is one thing, uh, which means that it's guaranteed, something is guaranteed present in the memory, and then cheaper, faster allocation. So you have more tightly packed memory and better locality, and you don't have the overhead of administering randomly assigned things all over the memory space, right? The driver allocation is a lot more simpler, and it's just more efficient, right? But we want to continue that discussion. So those are the two big benefits. Back to tying to selected code. So we have encoder, draw index primitives, MTL primitive, type triangle index, what have you, right? In a draw call that assumes every texture it might sample is already resident, right? The line you selected right here is a draw call that it assumes every texture it might sample is already resident, right? That assumption only holds because make resident for encoder was called earlier on line 291, which in turn only works cheaply because all those textures live in one heap, so in one block, right? Which we discussed in the previous episode. So the heap is what lets this draw loop stay simple. Bind texture at slot 0, draw, repeat. No residency bookkeeping per submesh, right? So again, our application has many textures, many materials, many things happening all at once, and we want to keep that loop, that process as efficient as possible. So, that's kind of why it is done this way using the heap. So I wanted to cover the heap discussion so that we had some context when we dove into the full process of what's going on with the textures. Think of new texture with descriptor on the device as renting a separate storage unit for every box. So new texture with descriptor. This is without the heap, individual allocation. New texture with descriptor. And then this is with the heap, right? We have one big block, and then we have sub allocations for texture, right? So think of new texture with descriptor on the device as renting a separate storage unit for every box. Lots of paperwork, and you must tell the mover about each unit. A heap is renting one warehouse and stacking all your boxes inside. One lease, one here's the warehouse key, hand off to the mover. Make resident for encoder, okay? Right here, this guy right here. And you rearrange boxes internally as you like. So that is our discussion for this heap right here. Want me to open APL Manager and show exactly where the heap is created and how the texture sub allocations. So yeah, let's just round it out. So heap is created in Texture Manager as heap is declared as an IVAR 123. So this is APL Texture Manager MM. And then 123. All right, APL Texture Manager. So we have our friend right here. Where is it? Right. So line 123, ID MTL heap, and we have our heap, APL Texture Manager. The heap is declared as an IVAR 123, right? So similar to what we have here. And then we have unordered map, hash texture lookup, okay? So note the two members that matter. Heap underscore heap, the memory, and underscore textures, this guy right here. So underscore heap and underscore textures, right? A C++ hash map from a texture hash to its MTL texture plus metadata. The material's base color texture hash is the key into textures, right? So there's this thing about a table where every material has like a texture hash, and then that texture hash is used to figure out what texture goes with that material. But note the two members that matter. Heap, the heap, underscore heap, the memory, and underscore textures. The material's base color texture hash is the key into textures. The heap is created once. So we have our variable here. $195 to $217. Okay. That's this guy right here. So we have heap size. We have a min function that's working on it. Don't exceed video RAM working set. So let's dive into this. This is the single expensive allocation, right? This is a single expensive allocation. Everything else just carves space out of it. Two details worth teaching. Storage mode equals private, okay? The memory lives only on the GPU side. The CPU can't touch it directly. That's why texture data is uploaded via a blit copy command later, not a direct memory write. Okay? So it's a copy, not a direct write, because I guess the CPU can't access. So that's storage mode. And then min clamps. So here we have our min clamps, min and min. The code refuses to request a heap bigger than the device's buffer limit or its recommended working set size, so it won't blow past available VRAM. The reason why this discussion is important is because, for example, I'm running on Mac OS. I'm running on a laptop, okay? But remember that these applications can run on your iPhone. It can run on your Apple Vision device, right? So that means iOS and Vision OS. So you need to make sure that the device that you're running on is able to handle your needs, right? Not only that it's able to handle what you are requesting, but that whatever you're requesting isn't above the recommended working set size for the device, right? So that's what these min clamps are for. And that's right. So we have limit heap size to device limits. So that's what this guy and this guy is about. And then we have the storage mode for the heap is private. And then the heap size, all that good stuff, right? And then we assert if there's a fail to create heap texture heap, right? So that's what all this is about. So let us continue. Each texture sub-allocates from the heap. So 979 to 990. This is a payoff of the heap. Create texture builds a descriptor and then this, right? So that's this guy right here. Create texture builds a descriptor and then Return new texture with descriptor, text descriptor. This is the actual. That one line is the whole point. Compare device new texture descriptor with heap. Okay, so right, we have heap new texture with descriptor. So device new texture with descriptor, a brand new independent allocation, what the fallback texture in the render uses. And then we have the heap version, right? Carved out of the already reserved heap block, no new memory requests to the driver. It just hands out a slice. Okay, so we're getting a slice here. All right. And then remember, guys, this is in APL Texture Manager. So we're still in APL Texture Manager. Create texture is called for every texture in the scene. So every texture within the scene, we have create texture is called for every texture in the scene in the add textures loop 437. So is that in this file? 437. So hundreds of bits of textures all end up living inside the single heap. Okay, add textures to a pre-allocated heap, decompressing the data from the data block. Okay, so it's this whole guy right here. So hundreds of bistro textures all end up living inside the single heap. Okay. All right. Look up hash texture. So remember we said we had a hash related to each material, a texture hash, and then we actually look up the texture for the material. So 385 to, so this guy right here. So get texture. When the renderer calls get texture, material.baseColor texture hash, this runs, right? Pure hash map lookup, no allocation, no GPU work. It just returns the MTL texture handle that was created from the heap back in step 3. So return it. Texture find hash. So constant auto it textures dot find, and then we have our hash. So get textures, and we have a hash here. We find it if it is not equal to textures dot end whatever. If our current map blah blah blah, return its second texture. If this doesn't ever return, then we return nil, right? And that's that. So let's get to, so this is the texture lookup situation right here. We'll dive into it, guys, don't worry, but we at least want to get familiar with some of this stuff right now. So residency, one call covers the whole heap. So 1000 Make resident for encoder, right. One call covers the whole heap. So all of this right here, just this right here. This is a reason a heap dramatically simplifies the render loop, right? Use heap, so this guy right here, tells the GPU every resource in this heap is about to be used. Keep them all resident. So resident means that it's guaranteed to be accessible and available in GPU memory. Without a heap, you need a use resource call per texture every frame, hundreds of calls. With the heap, it's one call made once per frame in APL renderer 291 before the submesh loop. So right, so it basically notifies the GPU that every, for this heap, make it readily accessible. It's in GPU memory, and we're ready to go. So if you followed that, guys, we could do here. So init once device new heap with descriptor underscore heap, one big private block. Load scene once per texture, add textures, create texture. Yeah, this isn't necessarily as clear as I would have hoped it to be, but as we get deeper into this discussion, we will we'll make our way through it. So the heap is relevant because it turns hundreds of textures, hundreds of residency calls into one memory block plus one residency call, and makes per texture creation nearly free. A slice, not a new allocation. The trade-off is you manage the sub-allocation yourself, which is exactly what create texture and the underscore textures map are doing, right? So yeah, we'll stop here with this discussion, guys. I just wanted to get you guys a little bit familiar with what's going on. So just real quickly, we messed around with APL texture heap. APL texture heap. We also did APL renderer. So in the renderer, it was make all textures in the heap accessible to the shader. This guy right here. I believe we did also APL renderer. So APL renderer, APL texture manager. I think we also did the header file too, right? Right. This is where the variable is set up, read only, all of that good stuff. And yeah, guys. So that is our discussion for the heap as it relates to textures. Okay, so we're a little bit more informed on what this is doing, and we are better for it. And then we could go through the full texture process, having understood what heap is doing and what heap is done. Just do a quick run through again, just so that we could kind of put everything together in our heads. I know it's very scattershot and disorganized, but we just have to spend time with it, and it will all be abundantly clear. So heap here means a metal resource heap. It's one big pre-allocated block of GPU memory that you can carve smaller resources, textures, buffers out of yourself instead of asking Metal to allocate each one independently. So you have a big slice of pizza that's your whole memory space. You cut out a slice and you make that your heap. And then inside of that, you could have sections of that slice that represent your texture related stuff, right? So without a heap, with a heap, without a heap, it's individual allocations across your entire memory space. There's driver administration and overhead related with that. Inside of the heap, you get things more tightly packed together. Locality, you save space, you don't have to remember as much administrative stuff even, because everything is just together and organized. The bistro scene has hundreds of texture calls. And we're trying to make that process as efficient as possible. We also have texture heap size, and we have to test to see, you know, first of all, can we request a heap size of X, and then also, um, is the working set for the device that we're on? Is it okay if we use a heap size of that size? Because if we're on an iPhone as opposed to a Apple Vision device, as opposed to a laptop, as opposed to a desktop, it might be different constraints. So you need to make sure that we do that. So the bistro scene has hundreds of textures, and we have residency is one big one. The GPU would only read a resource if it's marked resident, guaranteed present in memory for the command encoder, right? And cheaper, faster allocation. So reserving one bit block up front and sub-allocating is much faster than hundreds of separate driver allocations, and it packs textures tightly, less wasted memory, better locality. It also makes streaming practical, which we didn't get into in this one. So we have our draw calls. So the loop for the draw calls is a lot faster. Yeah, no residency bookkeeping and per mesh stuff. Right, so the quick analogy, which we want to go through again, new texture with descriptor on the device. That's like the individual allocations, across the whole memory space is like renting a separate storage unit for every box that you have. Lots of paperwork, and you must tell the mover about each unit. A heap is renting one warehouse and stacking all your boxes inside. One lease, one here's the warehouse key, handoff to the mover. And you rearrange boxes internally as you like inside of your warehouse. So instead of having many warehouses with one box in each, you just have one warehouse, and you put all of your boxes in that one warehouse, and you have one key that you can give access to the mover, so the mover can move the boxes into that one place. And it's not like you're moving all over the place to store the boxes. And then we get into, heap declaration, a one big memory block, and then we have our hash lookup. So all the materials have a texture hash, and that texture hash is just like it goes to a lookup table to say, okay, this texture hash is associated with this texture, and then we're going to associate that texture with the material that it's that we're working with, right? So it has a heap, and it has the texture, right? And then we clamp requested size to what the device actually uses. So right, this was a discussion about, we got to make sure that we don't exceed the VRAM working set for the device, and we're requesting a specific amount of memory. We also have the storage mode. So here is the storage mode is private, so it's private to the GPU. And then we have the min clamps, right? So we talked about the min clamps. Notice that it's heap, not device. So this is when we're using the heap, we're not using the general device memory space. And then this is looking up the hash, looking up what texture is for the hash that the material has. And then residency, so guaranteed that the item is in memory. We have our residency here. We have the full life cycle, which it's a lot. It doesn't. Yeah, so the heap is relevant because it turns hundreds of textures, hundreds of residency calls into one memory block plus one residency call, and makes the per texture creation nearly free. The trade-off is you manage the sub-allocation yourself, which is exactly what create texture and the texture map are doing. And that's it, guys, for this episode. I think I'm done with the heap discussion now, so we could move on to other things. But it was important that we We do this because Heap is used a lot in the texture discussion. This is Cuda Education, guys. You know what to do to support the channel. Thank you for watching. Have a great day.